control for the inverter inside, and you'll have a real inverter and motor outside. So this stage of validation is called rapid control prototyping. This will help you to refine or fine tune your control algorithms when it gets connected to a real equipment, right? So this is what is RCP. Next is hardware in loop. In hardware in loop, it is the other way around. You have the controller outside, you have a real controller, and you'll have a simulated plant, like here. I have a real controller here, and I'll be having a simulated plant inside the simulator. So this will help you to prepare your controller for the final tests. Before this controller goes for the final tests with the hardware, you can test this controller with a simulated plant. You can test it for a lot of other scenarios like different adverse load conditions or some fault conditions. You can test your controller, and then you can go for the final hardware implementation. So this is hardware in loop. We do have one more stage of validation called power hardware in loop. So in all the previous cases, whatever I said was whatever interaction you have between the simulation and the external world, that was a signal level interaction. So even here, I only have a signal level interaction between the controller and plant, between the controller and the simulated plant. But in power hardware in loop, you will have a power level interaction with your device under test. For example, let us say the device under test could be some traction inverter, let us say. So let us say it is you have a traction inverter which is going into an EV. So that traction inverter, it needs to undergo a test, it needs to undergo a power hardware in loop test with a simulated motor for different adverse fault scenarios and adverse speed conditions, let us say. Then you will need a power hardware in loop validation. You will need a power amplifier between your simulation and the DUT, which helps you to connect your simulation to the DUT at power level. Let us say you have a simulated motor and you want that simulated motor to exchange power with a real inverter which is outside, let us say. So that will not be possible with just the simulator and your DUT. You should have a power amplifier in between which helps you to do a power level interaction between your simulation and your DUT. So this is what PHIL is all about. Yeah, this is more a complex setup, and it is a more costlier setup as well, but still this helps engineers to test their DUTs before it goes for the final field implementation. So yeah, this is what PHIL is all about. So I spoke about model in loop, I spoke about RCP, rapid control prototyping, and I spoke about hardware in loop, and this power hardware in loop. So these are the different areas or applications where you will use this real-time simulator. Okay. Yeah, so I'll go ahead. So apart from this real-time simulator, we do have lot of software toolboxes which helps you to enhance your simulation experience. You can see we have eFPGA sim, as you can see. As I told earlier, eFPGA sim toolbox helps you to run your power converter simulation inside FPGA, and we have eMegaSim for power system simulations. And we have ePhaser sim for, again it is for power system simulations, but ePhaser sim will help you to import third-party power system models like PSSE, Power Factory and stuff. And we also have HyperSim. So all the other toolboxes, it needs MATLAB Simulink, but HyperSim is like a standalone simulation software made by Opal to do power system simulations again. Yeah. Depending on the application, we'll advise you which software toolbox will suit you. So yeah, these are some of the application areas where you will find real-time simulation. So yeah, now I'll go ahead with the demo which we have planned. I'll just show you the model. I'll show you the model. Let us say you have a simulation model and how to run that simulation model into a real-time simulation, into this real-time simulator. All those steps I'll quickly go around and I'll tell you. Okay.
So I have two questions.
Please.
There are a couple of questions from my side. Please ignore my ignorance about this thing. So I know very little about this. So I'll make some mistakes.
No problem.
First of all, is that you are talking about this PHIL. Now, when you're talking about connecting a hardware, that may be a induction motor or other motor devices. So you will be invariably using a PHIL there, because for this DSP controller that can be connected easily to the Opal RT. But when you are using directly a motor or any other heavy devices, those should be communicated to it through a power amplifier. So PHIL is a much more normal way of working.
Not necessarily. I can give you an example of an induction motor drive, let us say. So you have an inverter and you have a motor. So, and if you want to control the inverter through Opal RT, then you don't need, it's not like you will need a power amplifier in between. That is still a signal level interaction. So you will just have to take the voltage signals, give it as a feedback to the analog inputs, and it will further give out the PWMs to control the inverter. So this is still a signal level interaction, even though you have a motor and inverter. This is still a signal level interaction. Power level will come into picture when you let us say so let us say you have an inverter and you want to link that inverter with a simulated motor, and that simulated motor, whatever changes you see on the motor, you should see the change of that motor at power level with the inverter. So these kind of simulations will need a power amplifier in between. The other case which I said, you have only the controller inside the simulation, so it is not necessary that you need a power level connection between your plant and controller. So it basically depends on the application. It's not like you always need a power amplifier if I have an inverter or motor. It depends on the application.
So sir, one more thing is, can you give an example of this use of FPGA part in this Opal RT? So
yeah, what so FPGA will there are two roles for FPGA here. So one role for FPGA is to control your IO devices. Let us say you want to generate 100 kilohertz PWM, then you need FPGA. And other role is to run the plant model. Let us say you have a power converter which needs to be executed at 100 kilohertz. Then 100 kilohertz simulation will demand nanosecond time steps. So nanosecond time step will be difficult for your normal CPU or processor to achieve. So in that case, we'll need the FPGA into picture, and we'll run your power converter onto the FPGA, and that will help you to run more faster simulations and test it with the controllers and stuff.
Okay, thank you, sir.
Okay. I'll just
So you need to show some hardware connections and how you set up the model.
I'll quickly go around. So in this demo, we have a plant running, as sir explained initially. We have a grid forming inverter in MATLAB. So that is executed in this 5700 simulator. And we also have one control algorithm for this inverter inside this controller, which is placed outside. So I'll quickly go around. First, I'll go around with the plant model, and then I'll show you the. First, I'll show you the plant model. I'll tell you how to execute the plant model into real time and all those steps. Next one, I'll show you the controller model, and I'll also explain you the hardware connections involved between both. Oh, okay. Hardware connections I'll parallelly explain when I show you the models. So fine. So now I have the plant model here. So whatever plant model you are running or whatever simulation model you want to run in Opal RT, you do have some small procedures to run it. Let us say you already have a simulation model which is already validated in offline, your results are perfect. and if you want to run that simulation model into the polarity, you do have some very minor modifications which needs to be done to your simulation. So anyhow, we'll be able to guide you guys if you are doing that, but anyhow, to put it in a brief way, the top level of your simulation should have only subsystems like what I have here. One subsystem is called the master and the other one is the console. Master is a subsystem which will have your plant, whatever thing which is going to be computed inside the CPU, that will go into the master, and console is something which will help you to interact with the simulation when you are running it. So the console will have all the scopes and some control variables. If you want to change any parameters in the simulation, all those steps will have in the console. So now I'll show you the master, and also you should always make sure that your simulation is made with fixed time step solver. So here if you go to the model settings, so here you have the solver type. In MATLAB you have two options, one is the variable step solver and other one is the fixed step solver. So whenever you are running a real-time simulation, you should always make sure that your model is developed in fixed step solver. So that is one thing, and here you can see the plant. I have a DC source here and I have this inverter which is acting as a grid forming inverter, and I have an LC filter here, and I also have the infinite bus. We also have few a resistive load here to connect and disconnect, and we also have one fault system here which will help you to insert fault and see how your controller is behaving. So now this is the plant. Now you have the controller outside. To this inverter which you have here, the PWM for this inverter is going to come from this controller which is outside. So to do that, we need to first send the feedback signals from this simulation model to the controller which is outside. So you need to configure analog outputs on this simulator to send the feedback signals. Yeah.
So if you compare this diagram with that, so the inverter is basically a 3-leg inverter, 2-level 3-phase, okay? And you have there are 6 switches, and we discussed DC-DC converter. This switch pulses has to come from the controller, okay? Thank you.
Yeah.
Plant is whatever power circuit you see is the plant. Apart from controller, whatever you see is the power circuit, and we call it, in control system language, we call it plant.
Okay. Yeah. So now if you want to link the external controller with this simulation, you need to send some the feedbacks to the controller, right? So currently your current controller will need the 3 grid voltages and also the currents which is after the filter and before the filter. So you have a filter here. So all these feedbacks we need to send. So I am adding the measurements inside. I'm adding the current and voltage measurements in the model, and you still need to do some signal conditioning to meet, because our analog output is rated. Our analog output you can send only plus or minus 16 volt, and also this controller can take a plus or minus 10 volt for taking the feedback. So accordingly, you do the signal conditioning here, and you send it to the analog output. So here we have this analog output here. This is an analog output block which helps you to configure the analog output which you have in the simulator. On the back side of the simulator, we have the analog output. Maybe in the break you can come and see the connections once. So from the analog output, I'll connect all the feedbacks to this to the analog input of the controller through this connector. So this is the analog output configuration, and in turn, after reading these signals, this controller will run the control algorithm and will give out the PWM through digital output, and that needs to be fed to digital input of the simulator. So you can see here I have a digital in. This digital in block will read the PWM generated by the external controller, and that is fed to the inverter inside. So inside the subsystem you have the inverter, and you can see all the 6 PWMs are taken from digital input and it is fed into the inverter. So this is how you modify your simulation in such a way that it is ready to be tested in HIL. So you go through the basic procedures I said, grouping into subsystems, changing the solver and all those stuffs, and you configure analog outputs and you configure digital inputs for this application. So now this is what plant model is all about. Now I will go into the controller model. So this, I have this controller OP8666. This controller, it is nothing but inside the controller you have the TI F28379D card. So to run the models in this controller, you need to So to run your models inside this controller, you need to first install the MATLAB C2000 add-on. So there is a library add-on in MATLAB which you will find, which is specially for the Texas Instruments C2000 control boards. So you need to install that, and you need to take some custom block sets. So the first step in your controller model is, you have the control logic here. This is the control logic inside it, you can see. So this control logic and the plant is developed by one of the students of sir. Now to run it in this controller, you need to additionally configure the analog inputs here on the controller. That means ADC. You need to configure ADC modules in the controller. ADC is the one which helps you to configure the analog inputs of the controller, and it will help you to bring the signal which you have outside into the controller. So you can see the ADC modules here. See, I have the ADC modules here with I have around 3 plus 4. Yeah, I have around 7 ADC modules because we have a total of 7 signals. We have 3 voltages and 2 currents before filter and 2 currents after filter. So that's what this ADC module is all about. So when you are configuring ADCs, you need to make sure that which ADC modules controls which channels in your controller. So we do have few pin diagrams for that. Accordingly, you need to configure ADC, because if you see inside it, each ADC will have different modules A, B, C, and D. So which module you need to configure will depend on what channel you are using. So all those steps this controller has its own pin diagram configuration. So accordingly, you will be able to configure it. And after configuring the ADC, here you will get the signal, but this signal is again, it is the ADC output. It is still not your real signal. So you need to do again you need to again add some gain factors and offset factors, because inside this circuit we do have some offset circuitry and gain circuitries. So to bring back the original signal from this ADC signal, you need to once again have some signal conditioning here. You can see I am adding some offset and I am adding some gain values here. This offset and gain is something hard coded and it is fixed for this controller. So whatever signal you are trying to take from your external analog input, you need to multiply with this gain and offsets so that you get the actual signal after that. It will also depend on the resolution of your ADC, like whether it is a 12-bit ADC or 16-bit ADC. You need to configure the gains accordingly. So these are hard-coded values, which is particularly for this OP8666 controller. So this will depend on for other controllers. So you need to go through the manual of that controller and you need to find what is the offset, what is the resolution of the ADC, all those steps you need to find, and then you need to do the math to get the actual signal from your ADC module. So here you will get all the signals which, so now whatever signal, these signals will come from your OP5700 simulation now, because from the analog out we are connecting it to analog in and we are retrieving the original signals here, and these signals will go to this controller. You can see inside this you have the control logic happening, and this controller will further give you the duty ratio or the modulation signal. So that modulation signal you feed it to this PWM block. So again, this PWM block is something which is particular for this 28379D card, the TI278, the TI card which you have here. So this block will come from the same C2000 library which you will install in the MATLAB library. So you will use this PWM module to generate the PWM. Now this PWM will go to the digital output of the controller which you have physically here, and that will be physically routed to the digital input of your Opal RTM 5700 simulator through the connection which we have here. So in hardware perspective, we have two connections: analog output from 5700 to the analog input of the controller, and digital output of the 8666, the controller is connected to the digital input of this 5700 simulator. So these two connections you have, and yeah, this is what the control model is all about. So now we have the control model and we have the plant model. How do we run it? So for running the controller model, we are going to follow the automatic code generation option which is there in the MATLAB. So that is the advantage of using this TAC2000 board. So you can just click this build option here. The moment you click the build option here, automatically MATLAB will generate a code for that, and you need to launch Code Composer Studio. So Code Composer Studio is a software made by TI specifically to dump codes onto the TI cards. So in MATLAB itself you will have an option to launch Code Composer Studio. You can see here, open Code Composer Studio, you can have that, you can see that link. Through that you will launch Code Composer Studio and this window will open. So here you will have the automatic code which is generated. You can see here. So now using this Code Composer Studio software, I will be dumping it onto the controller. So here you have the debug option here. If you click the debug option, the code will be loaded onto the controller. Let's wait. Okay, parallelly when it loads, I'll also show you our RTLab environment. So when the code loads, I'll show you this one. So this is the RTLab software which helps you to run your MATLAB models into this simulator which you have here. So in RTLab, you have three options. You need to first import the model. I already have the model imported here. You can see there that sine limiter, whatever. So that is the model which I have imported. So you need to build, load and execute here. So you have the build option, and you should also add the target. The target is your simulator. Every simulator comes with its own IP address. So your host PC will communicate to the simulator through the LAN cable. So you can, the advantage here is you can keep the simulator over the network and you will be able to access the simulator from anywhere in your anywhere whenever you are connected to the network. So that is why you add the target here corresponding to your IP address. So that is the IP address, but you add the target, and then after adding the target you bring in the model, you build, load and execute. So building is the stage where the model will, the RTLab will generate the code, and loading is the stage where it will dump the model, and execute means model will execute. So anyhow, I have already built, loaded and it is executing. So the build, load and execute options are here, as you can see. Now all those options are grayed out because I have already done it to save some time. Now you can see the model is running here, but now the controller is still not loaded. So let's go and run the controller, and then we'll come back here and we'll see how the results are. Yeah, so here the controller is loaded. I'll just run it. So here I have added the control variables here in CCS. All the analog inputs which I am reading, all those stuffs I have added it here. Now you can see all those variables, all those variables are reading a unit sine wave. If you see the value in this section, it is toggling, it is varying from -1 to +1, because currently in order to just test whether the analog inputs are working properly or not, I am just forcing some sine wave to see if it works or not. So that is what it is. Currently you are reading the forced sine waves. Now in the plant model I will be switching to the actual feedbacks of the inverter. See here the plant model is running. So here I have the option to switch between the forced signal and the actual signal. So now I will switch to the actual signal. So now the actual plant feedbacks are going to the controller. So now you will see the control happening. You can see the grid voltages and grid currents here. So there are two ways to monitor. Again, you can either monitor it through the scope which you have here, or you can also monitor it through RT Lab. Maybe I'll show you that first. Let the scope open. Yeah, you see the voltages and currents. You can see the sine waves here. You can also monitor it through software from RT Lab called Scope View. So normally I use that for seeing it. Now I'll launch that and I'll show you all the three results. I mean, I'll show you the grid current, grid voltage, and also the inverter's current. All those three we can see now.
So you have 5 minutes.
5 more minutes? Yeah, we can wind it up. Yeah, now you can see the all the three signals here. I can just quickly turn on the load. I have the switch to turn on the load here. If I turn on the load, you will see more current flowing. Now if I click run, you will see the current magnitude will increase. Yeah, now you see the current magnitude has increased from 1 to 2 and the grid voltage has slightly dropped. But anyhow, so yeah, this is the HIL demo of the grid following converter. Sorry, grid forming, sorry. So if you have any questions, I'll be happy to answer, or we can discuss afterwards also. And we can, so this is my contact, this is my email ID. If you want, you can note my email ID and I'll be happy to respond to all your queries. So.
Okay, so I know there are so many questions, but due to time, we'll keep it for later. But you have already contact number of him, or if you want to know more, you can also contact me. And Yeah, so this is basically one demo. So you can think of, let's say you have a DC-DC converter control also. You can add to the plant model and also create the pulses through the 8666 controller for that also. Okay. And thank you so much, Siva, for your time and agreeing in this short time and coming here. And at least people are more interested to real-time simulation. So be ready, you will get more questions.
Yeah, I'll be around. You can reach me at any time.
So he will be in the lab in the afternoon. So any connection, anything you want to see, you can see after the closing ceremony. So thank you. So as per the plan.